The formula for the sum of an infinite geometric series. I'm going to give you the formula and the criteria, and then we're going to look at the proof for that and work on that together. We have the sum of CR to the n, so that is our geometric, and we're going to start it at little n equals 0, and it will go to infinity. That sum is going to be equal to C over 1 minus r. People commonly try to remember this, and this really well, as first term over 1 minus r. So if you plug whatever number little n starts at into the formula, that would be your first term. And that will work no matter what little n you start with. So you can start with n equals 3 or 4 or 1. And this will always work. This will also work in the case of little n equal to 0. So it's probably easiest to remember this as first term over 1 minus r. It will converge if the absolute value of r is less than 1. So we would be looking for values of r between -1 and +1. And it diverges if the absolute value of r is greater than or equal to 1. The proof for this, we're going to split this into two cases. So case 1, I'm going to look at r equal to 1. And for case 2, I'm going to look at r is not equal to 1. That covers all the possibilities. R is either 1 or it's not 1. For case 1, this is going to look like the sum of 1 to the n, which is 1 plus 1 plus 1, and you just keep adding 1 forever and ever. That is definitely going to infinity, and it diverges, which matches our criteria up here. That's a good thing. And then case 2. So for case 2, I brought our limit over from the previous page in the previous video. We have s is equal to the limit as big N goes to infinity of s of n, which is c, so we pulled our constant out in front, times the limit of 1 minus r to the capital N plus 1 all over 1 minus r. The first thing I'm going to do here is I'm going to split this into two fractions. So I have c times the limit as capital N goes to infinity of 1 over 1 minus r to the capital N plus 1 over 1 minus r. And now I can apply my limit term by term. So 1 over 1 minus r doesn't have an n in it. So that'll give me, I need to distribute that c, so I have a c over 1 minus r. This second term does have an n in it, so I need to keep the limit. I get minus c times the limit as capital N goes to infinity of r to the n plus 1 over 1 minus r. And I'll pull this constant out in front, so I get c over 1 minus r minus c over 1 minus r times limit as capital N goes to infinity of r to the capital N plus 1. So I've managed to isolate my limit here. And I'm going to look at two possible scenarios here. So the first thing I'm going to look at is, I'm going to call this case 2a. And that's going to be if the absolute value of r is less than 1. If that's the case, then the limit as capital N goes to infinity of r to the capital N plus 1 is 0. That means that s, I'm going to plug 0 in for this limit, s is going to be equal to c over 1 minus r minus c over 1 minus r times 0. That second term goes away, and I get that s is equal to c over 1 minus r, which means that it will converge if the absolute value of r is less than 1. That matches the definition that I gave you up here, so that's a good sign. And case 2b is going to be if the absolute value of r is greater than or equal to 1, but r cannot be equal to 1, because we already covered r equal to 1 in case 1. So that's already been dealt with. So I have r, the absolute value of r is greater than or equal to 1 as long as r is not itself 1. Then I can reevaluate this limit. So the limit as big N goes to infinity of r to the capital N plus 1 does not exist. That means that S does not exist. And in this case here, where the absolute value of r is greater than or equal to 1, the geometric series is going to diverge, which again matches the definition that I gave you up here. So that's our proof for our sum of an infinite geometric series and whether it converges or diverges.